Hello, and welcome back to our course, C++, a general purpose language and library. When we left off before the break, we were talking about some of the basics of objects in C++, and some of how the basics of classes work. In this lesson, or in this module, we're going to be going over references, which are another way of dealing with objects, and we're going to be dealing with some more advanced class topics, including inheritance and polymorphism. So that's basically our agenda for the module. So first we're going to talk about references. So far, all of the things that we've seen have been objects. So, when we had this initial example, we had two objects, x and y, and they're completely independent. So we could change the value of y and it wouldn't affect x. So, for example here, we changed the value of y, and even though we initialized y from x, we were copying its value. So in C++, we can also use references, which enable us to give another name to an object. So to declare a reference, basically we just append an ampersand to the type name. So for example here, we have an object x, and then we have a reference to that x object named xref. You can tell it's a reference because it has the ampersand. Anytime you see something, type name that's followed with an ampersand, it means this is a reference. So what does this mean? Well, it basically means that anywhere we use xref, it's as if we were using x. So for example, we can still use x. We can assign the value 2 to it, and the value will change. But also we can use xref. We can assign 3 to xref, which will actually change x to have the value 3. Further, we can use it as an r value on the as an initializer for y. So it's basically as if anywhere we were saying x ref, we're actually saying x. So why is this useful? Well, we can consider one really obvious example when we're calling functions, and we kind of saw some of this in Module 2. So let's say we have a function called multiply by 2 that takes an integer as a parameter, and we take that parameter, we multiply it by 2, and assign it back to the parameter. If we call this function, as we saw, the x with which we call it, it's not modified because we're actually passing a copy of the x. C++ is passed by value by default, so we're passing the value of x, we're making a copy. So what we can do to make this work, if we didn't want to have multiply by 2 return the result, is we can change that parameter to be a reference. So now, because it's a reference to x, the slide is incorrect. The x will actually equal 2 at the end of the function because we'll actually be modifying the x that we passed in. Basically, in that function where we say parameter, it's as if we were replacing the x from function f, even though there's no way for us to actually say x in that function because it's in a different scope. So there's two other important things about references that we'll note before we go to a demo. The first is that references must always be initialized. So if we have a reference and it's not initialized with an object, then it's invalid. The compiler will give you a compilation error. Once a reference is initialized, you can't change the object to which it refers. So for example, if we had two ints, x and y, and then we had an xref that referred to x, we couldn't suddenly change it to refer to y. There's no way to do that. It always refers to the object with which it was initialized. So the second important feature is how references interact with the const qualifier that we introduced. As we saw in the last module, an object can be const qualified, which means that it can't be modified. So, if we have a const int, we can't change the value of that integer. A reference can also be const qualified. So, for example, if we have a const int, then we can have a const reference to it, which means that anytime we use that reference, we can use it to read its value, but we can't actually change it. So here, for example, we're using x to initialize y. Now, this might not seem very useful for integers, and indeed it's not particularly useful for integers, but it is more useful for class types where you may have const member functions and you want to pass a class by reference and only be able to call const member functions. This is actually a very common thing in C++ to avoid copying large or expensive to copy objects, and we'll see some more of that later in this course. So the other important thing is that you can bind const references to non-const objects. So we'll take a look at that here. So here we have an object x that's not const, so we can change its value. And we've declared two references that both refer to that x. One of them, xref, is not const. The other one, xconstref, is const qualified. So what this means is anywhere that we're using xref, we can modify the object via that reference. But anywhere we're using xconstref, we can't modify that object. So this also fits in, again, with the const qualified member functions in that we can't what was I going to say? We can't. You can't make. You can call const member functions via a const reference, but you can't call non-const member functions or otherwise change the object. So I don't have a demo slide. Do we have a demo for this?
Sure.
Excellent.
I can prove that some of that code on your slides
that would be wonderful.
Really does work. Yeah. I'm going to show you another way to get this thing started. You know, we've been clicking here to make a breakpoint and then clicking up on the green play button to run to there. But just to show there's lots of ways to do everything, you can also right-click any line and say run to cursor, and it'll go to there without leaving a breakpoint in that place.
I just learned something here.
That's my favorite way to jump forward 3 or 4 lines, too. So we'll start with integers that are not const or references or anything, just to make this really clear how this is going to work. So here when we initialize x to 1, and we initialize y using the value of x, they're not connected to each other in any way. They both happen to have the value 1 right now, but they occupy different pieces of memory, and they don't have a permanent relationship. So when I change the value of y, x remains unchanged. Now I'm going to make a reference to x called xref. And this ampersand specifies that this is now an integer reference. Whether I talk to it through x or whether I talk to it through xref will have exactly the same effect. So if I step over the line that says x equals 2, not surprisingly, x becomes 2, but so does xref. And when I step over the line that says xref equals 3, xref becomes 3, and so does x. So in both of these, the name is just 2 names for the same piece of memory, the same place in memory. But if, just as with x and y, using one to initialize the other, when I initialize this copy passing in xref, that's a different piece of memory that just also happens to have the value of 3. Now let's get into our const sample. In this version of the const sample, the multiply by 2 function takes its parameter by value. It's just an integer. So if I run to here, and step over multiply by 2 of x, x is still 1. Because basically what happened is we gave 1 as a copy to this function, it doubled it, and then when it reached the end of the scope here, it threw the copy away, and life carried on. If I now change this function, just by typing this single character, why are you unhappy? I'm going to ignore that. And we'll run again. X is 1 before I call the function, but after it becomes 2. So this single character makes a big difference in the behavior. Now, just as x and xref in the previous demo were really just 2 names for the same place, in this call, parameter and x are 2 names for the same place. And when we change parameter, we change x. And James mentioned that you must initialize references when you declare them. If I uninitialize, let's leave this guy sitting around, you notice I immediately get a red wigglies. It says requires an initializer, and if I build it, same thing. References must be initialized. So you can't forget the rule. The compiler's your friend. It will help you out. So now let's play with const. This is an integer reference to x. Neither this reference nor the underlying x are const. So I'm welcome to change them if I want, either through x or like this with xref. But here, xconstref is a constant reference. Now, in real life, you would not be putting words like ref and const into your variable names. We're doing that to emphasize to you what they are, just as you don't have very many real variables with names like uninitialized. Your real variables will have these qualifiers like being const or being a reference, but they won't be labeled as that in their names. They'll have names like next employee hire date or something. So let's run through to here and watch what happens. When x is currently 2 because we took 1 and we doubled it, and if I want to go and put 2 in it, I can. Nobody complains. Whether I come at it through x or xref doesn't matter. But if I uncomment this line, it won't build because I really hate this error, by the way. Must be a modifiable L value.
Yes.
However, if I compile it, it's much better. You cannot assign to a variable that is const. Because although x isn't const, the ref I'm using to access it is. And the compiler says, you promised you would not change that. And here you are trying to change it. So there you go. The compiler is our friend.
Yep. Similarly, it would not be allowed, you cannot bind a non-const reference to a const object. So if we have a const int x, we could not have xref that's not const bound to it. Because then you would be telling the compiler, hey, I have this object. It's const. It's never going to change. But then I have this reference via which I could change it. So it doesn't make any sense. So that is prohibited by the type system. The compiler will forbid you from doing that. So
there you go. Const object must be initialized if not extern. It's really unhappy. Oh, it's because I didn't give it a value. Why is he happy? Oh, because I didn't use him yet?
That's
a const reference to a constant. That's fine. Now let's make a non-const reference to a content, and now we get an error.
Yep.
And it says I can't convert from a const integer to an integer reference. So always the compiler tells you what the problem is. Sometimes it can be a challenge to interpret what it's saying, but in this case, it's pretty easy to trigger the errors and see what messages you get for them.
Yep. And again, your favorite search engine is your friend for those. You know, being able to go and search for, especially those that is 4-digit error codes, extremely useful. And if not, if MSDN doesn't have the answer, then certainly other question and answer sites like Stack Overflow would. So, okay. So that's the basics of references. We've actually introduced them because they're going to be a prerequisite for understanding the next piece of what we're going to show off, which is inheritance. So far, we've seen our rectangle class, which is just its own class. It has no relationship to any other types. So C++ supports one of the main features of object-oriented programming called inheritance, which allows a class type to inherit behavior from another class. So we're going to see an example of that involving our rectangle type. And we're actually going to start off with the demo for that because there's a bit of code to show off, and it's hard to put into slides.
So here I have another project open that is going to exercise a class, but before I exercise it, let me show you what it does. Here's rectangle, who you met before, with its private width and height and its public constructors, get width, get height. You can see why you don't necessarily want things in the header file. They tend to go on for a while. A resize function and an area function. And this is exactly the same as we showed in earlier demos earlier today. But then we have named rectangle. And named rectangle is a rectangle with a name. The name is going to be represented as a string, and the syntax for saying this is a rectangle with a name happens in this line here at the top. We say class, named rectangle, colon, public rectangle. The public is what you always say. Historically, you used to have a choice, but trust me, you just always say public rectangle. And then down here in the private section, we list the name, which we're going to make of type string. In order to use string, we've included string up here in the top. In order to use rectangle, we've included rectangle. And to take a small aside, because these two lines happen to be sitting next to each other, you may have noticed there's different punctuation on the two lines. So when we include rectangle, we're using double quotes. And when we include string, we're using angle bracket. The mechanics of this are that it directs Visual Studio to look in a different folder. The things with the quotes, it looks in your project folder. The things with the angle brackets, it looks in, let's call it a system folder, where the standard library can be found. So string is a class in the standard library that we want to use, so we include the string header with angle brackets and rectangle with double quotes.
Yep. So in general, you should always use angle brackets for the standard library or third-party libraries you may be using, or if you're using the Windows SDK, you'll use them for that. But always use quotes for your own headers generally.
And you'll notice the pattern that the rectangle class is defined in rectangle.h, the named rectangle in named rectangle.h. Again, no one's going to enforce this on you. The compiler isn't going to make you do it. But you know, they say you should always write your code as though it's going to be maintained by a psychotic axe murderer who knows where you live. And if you put your rectangle class in something called stuff.h and I have to maintain it, I will track you down. So it's a pretty good plan to have one class per file and to give the file the same name as the class, just so we can all kind of live happily. Now, in inheritance, when I say that a class like named rectangle inherits from rectangle, that means that rectangle's height and width are also inherited down into named rectangle. So a named rectangle has a height and a width. You don't see them listed here because you don't have to list what you're getting from the class you inherit from. We typically in C++ talk about the base class, that would be rectangle, and the derived class, which would be named rectangle. The OO people will say superclass for rectangle and subclass for named rectangle, and that's okay too. They're both legitimate words for what's going on here. I'm not going to walk through all of the code for named rectangle just now, except to say that I only have to write the things that are special and different in named rectangle, and I get everything that came in from rectangle without having to write. For example, you don't see area anywhere in here. However, I can make myself a named rectangle. This one happens to have the name Fred, and then call area on that rectangle. The reason I can do that is because a named rectangle is a rectangle. So let's just prove this works. If I step over this line, we can see our named rectangle Fred rectangle with his width that came from rectangle, width and height, and his name that came from being a named rectangle. And if I step over this line, hopefully no one's shocked that this is 12, which is the area of a 3x4 rectangle. Now, remember when we had doubles like 3.2 and 2.9 and we put them into integers? They had extra information that got thrown away. Well, that's exactly what this next line of code is doing. I have this Fred rectangle, which has a width and a height because it's a rectangle, but also has a name, and I'm putting it just into a rectangle. And the compiler does not have a problem with that. When finished, unnamed rectangle has this width and height. It doesn't have a name, it doesn't have anywhere to keep a name any more than the integer had anywhere to keep the fractional part of the value. But this is an okay thing to be able to do. Mm-hmm. Now, what if I instead make a rectangle reference? Well, it's just like when we had an integer reference. You can work through it the same as working through the original thing. So after I set up this Fred ref to refer to Fred rectangle and I call resize, Fred rectangle, let's hover here, has resized to 6x8. So going through the reference changes the real rectangle the same as it did with everything else. And of course, I can continue to call area on that rectangle. However, you see the line that's commented out? This is a rectangle reference. It doesn't have a name, getName method, because rectangle doesn't have a getName method. If I want to call Fred rectangle.getName, I totally can. And it successfully pulls back the name Fred, because Fred rectangle, way up here at the top, is a named rectangle. But FredRef is not. He's just a rectangle. So if I stop debugging and uncomment this line, it won't compile. Okay. And, oh, I'm getting a redefinition because I have two lines the same. Let me comment that one out. GetName is not a member of rectangle. And that's the truth. It's not. If you want to get hold of a named rectangle using a rectangle reference, you can, but then you can only talk to it as though it were a rectangle, because that's what you think it is.
Cool. So basically, the key here is that a derived class has all of the member variables and functions of the base class. So when we say So in effect, every named rectangle is also a rectangle. It has, a whole rectangle object inside of it. It has rectangle parts. And a reference to a base class can actually refer to a derived class instance as well. So we saw this when we had a rectangle ampersand referring to a named rectangle object. But when we do this, it refers only to the base class pieces of it. So it doesn't have any knowledge of, it's actually this derived class type. So we can take a look at how this looks in memory. So if you remember, we had our rectangle object that has a width and a height, and our named rectangle is basically the same. It has a rectangle, which is called a base class subobject because it's a subobject, a piece of the whole, and it comes from a base class. And then it has an extra name, and so we actually, that's a data member, and we've called it a member variable. It's also called a data member subobject because, again, it's a part of the whole. And the named rectangle encompasses this entire piece. So when you bind a rectangle reference to a named rectangle, it's actually just binding to that blue and that orange piece. It's binding to that rectangle piece of it. In order to use the named rectangle, you have to have a named rectangle expression or a reference to one or an object. So what happens, so as we saw in the example, it's possible to take a named rectangle and use it to initialize, or you can assign it to just a regular rectangle object. But there's no room in that ordinary rectangle object to store the name. Like as we can see here in the picture, there's only room to store a width and a height. So what happens is the object gets sliced. Basically, the pieces that don't fit, we end up throwing them away. We're like, we can't store that. So this is a common problem that people run into, especially beginners. It's like, hey, what's happening to my objects? They're changing type on me, or I'm losing, important information. So you should always be careful of this. That you should always, if you're ever referring to, some derived class object via a base reference, which we end up doing a lot, as we'll see in the next lesson. You need to be very careful to make sure that you're always doing it by reference and not making copies. The reason that it's possible to make these copies, these sliced copies, is actually for the same reason that it's possible to bind the reference in the first place, is that you can have a derived class and you can convert it to its base class subparts.
Yeah, by just throwing away the extra stuff.
Exactly, yeah.
But it's rarely what you wanted to throw away the extra stuff.
Yep, it's usually not what you intended, right? So that's inheritance in a nutshell. Now, inheritance in itself isn't really sufficient to get what we want. Like, certainly it's great for code reuse because you can take commonly used code and put it into a base class and derive many things from it. Like, not only could we derive named rectangle, we could have a color rectangle that could have blue or green or whatever color that goes with it, or anything like that. But this is not useful. What it's not useful for is if we have different types of objects, like if we have a rectangle and a circle and a triangle and a pentagon, and we want to have different ones of these and be able to deal with different ones of these, and they all may have a get area function. Because you can compute the area of each of these types of shapes, but the actual implementation of that get area function is different for each of those shapes. I mean, the math that we have to do to compute the area of a square is very different from the math we have to do to compute the area of a circle. So dealing with different types of shapes or different types of objects requires what's called polymorphism. And so we're going to do a demo now to show off some of the details of how that works.
Sure. So I've got quite a bit of code here that's going to exercise my various classes, but you may notice if you look in the Solution Explorer on the side, there's an awful lot more files going on in here. So let's start with named rectangle again. It looks the same as before. It still inherits from rectangle. But rectangle has changed a little bit because it now inherits from something. There's a reason for this, which I'll show you by showing you shape. Shape has an area function, and it's fully decorated. For now, shape has an area function. Why do I need it to? I want to be able to talk to rectangles as though they were shapes. I want to be able to talk to triangles as though they were shapes. and to be able to call their area method. Right now, I can only call area on something that has an area method. So named rectangle and rectangle both have an area method. And my triangle here has an area method. But I would like to be able to call area on any shape. And in order to do that, I want to add the area function into shape. This keyword here, virtual, sets C++ apart from some other languages. This turns on polymorphism for this picture, for this class. There's a small cost to polymorphism. It allows base classes to have one implementation and then derived classes to change the implementation. And virtual is therefore chosen by the developer or not. In addition to being virtual, this has extra decoration, which is this equals 0. Imagine I set you the task. Please write me the code for shape's area. You can't do it. As James said, the formula is different for a circle, for a triangle, for a square. We don't know shape's area function. And this equals 0 effectively says to the compiler, and I won't be giving you any code for it. We call this a pure virtual function. Now, why would I possibly want to write a function and then not include any code for it? Because it allows me to insist that this is a function in shape, even though there's no code for it. Then anytime I have a shape reference, I can call area. How can you call a function that there's no code for? As long as each of the subclasses implements it, the compiler will correctly call the subclass or the derived class's version of area. So named rectangle doesn't need an area because he inherited it from rectangle. Rectangle has area, width times height. Triangle has an area, in here somewhere, width times height divided by 2. This is a right-angled triangle. I can then take a shape reference, and whether it's really referring to a triangle or really referring to a rectangle or named rectangle, call the area method and get the right thing to happen. Up here, I wrote this function called compute area, and it takes a shape reference. In fact, like most functions that take a reference, it takes a const shape reference because we don't intend to change it. So if someone wants to give us a const one, we should play nicely with that. So compute area takes a shape reference, and it can call area. Because area is virtual, if I give it a triangle, it'll call triangle's version of this function. If I give it a rectangle, it'll call rectangle's version of this function. And that's exactly what's happening down here. I have a triangle, which is 2 by 2. And good old Fred is still kicking around. He's 6 by 8. And I've got this line of code that's going to call compute area and pass in Fred rectangle. And this line of code that's going to call compute area and pass in triangle. Because it's a shape reference, and because a triangle is a shape and a rectangle is a shape, the shape reference can bind to these derived classes and will use their versions of the code. So if we run down to here, we step over this line. Fred's area is 48, which is indeed 6 times 8. And triangle's area is 2, which is indeed 2 times 2 divided by 2. So we've successfully passed in different solid objects, one a rectangle and one a triangle, to a function that's only expecting a shape reference. That shape reference only has access to member variables or member functions that are in shape. And shape is very boring. It has one thing in it, which is area. But that's all we need. We're able to call area on the shape, and then we get this nice polymorphism.
Okay.
Do you want me to uncomment the lines that won't compile?
Absolutely. I love listening to the compiler.
The lines that won't compile are always the fun ones. Sometimes when I want to explain pure virtual functions and abstract base classes, I say, tell me what kind of bank accounts your bank offers. Someone will say, oh, saving, checking, retirement. I'm like, good. Go on in the bank and just open an account. But I don't want it to be a savings account or a checking account or a retirement account, just a plain old ordinary everyday account. And it's strictly a thought experiment. I wouldn't actually try to do this in the bank because, you can't. You can't have the general base object of account. And in the same way, we can't make a shape object. The compiler doesn't issue any like value judgments or anything. It's simply a matter of this function being pure virtual. If you refuse to provide the code for a function, then the compiler won't let you make instances of the object because somebody might call it. And that's what's happening here. It says object of abstract class type shape is not allowed. Function shape area is a pure virtual function. Which is surprise, I'm getting a readable error message from the hoverovers and not just from the compiler.
Absolutely.
It's excellent.
We try.
Yeah, it's well done. Pass along my compliments.
Will do.
So this is a fully expected error. Not all base classes have a pure virtual function in them, but if they do, then they become abstract and you're not allowed to create instances of them.
So for example, the rectangle class is a base class because it's the base class of the named rectangle class, but it's not abstract because it implements all of the virtual functions. It has no pure virtual functions left.
Right. So we're allowed to create instances of just rectangle if we want to. And if we then want to try to initialize a shape by copying in rectangle, saying, oh, maybe the problem was the default constructor, again, we're getting these error wigglies because you cannot create an object that is of type shape. If you really wanted to, then you'd have to go implement area, but good luck with that because I don't know how to do that.
Yeah. Yep.
Go ahead.
All right. So basically, virtual functions can be overridden by derived classes. So that's what the process is called, overriding. Pure virtual functions must be overridden by derived classes. So we saw that with the abstract class that had the pure virtual area function, our shape class. There are some classes, like our shape class, that have no implementation at all. Like they're all pure they have only pure virtual functions. These are often called interfaces. Some languages have like a special interface keyword to allow interface inheritance to be special. In C++, that's not the case. We just have a base class. Sometimes it's prefixed with the letter I is common, the capital letter I. But it's really just a base class with virtual functions. The fact that it has no data and no implemented member functions is not relevant. So you can call code that has a reference to the base class can call a virtual function and end up calling the implementation in the derived class. So with ordinary member functions like our get width and get height that we had in rectangle, or our compute area function that isn't a member function at all, the compiler goes and actually figures out which function is going to get called at compile time. So when it compiles, it knows, I know exactly this function is going to be called. I know this will be the exact function. But with virtual functions, it doesn't know, because you could pass, if you have a reference to a shape, you could pass in a triangle or you could pass in a rectangle. And so it defers that decision until runtime. And so it actually looks at it and says, this is a triangle object. I'll call the triangle implementation of area. Or, this is a rectangle. I'll call the rectangle implementation. So this is more expensive than calling non-virtual functions, which is why it's optional to make functions virtual. It's more expensive because it actually has to go and check, this is the type of the object. Now, it's not particularly expensive. I mean, you can certainly use virtual functions without fearing that you're going to, make your application perform slowly. But in high-performance code, it's something that you might consider avoiding. But it fits in well with C++'s general philosophy that you only pay for what you use. So, if you don't need that polymorphic behavior, then you don't pay that extra cost of having to call, virtual functions. So this is a very powerful technique. Like, you can do a lot of amazing things with this. You can also do a lot of horrible things. There are many applications that have enormous class hierarchies of, classes with 12 levels of inheritance and functions overridden. So you should be very careful when using this. So certainly there are problem domains where it makes sense. It's a very important feature of C++. It's used in many libraries. It's used especially on Windows. We use it in COM, which is this enormous C++, largely language independent, but primarily C++ framework. But you have to be careful because every virtual function is an extensibility point. So every time you have a virtual function, someone could derive from your class and go and change, the implementation of what gets called. So it expands the surface area that you have to test for, because you have to, make absolutely certain that, you could plug in any possible behavior and the rest of your class still works, consistent with how people expect it to work. So if you have classes that implement hundreds of virtual functions, the amount of stuff that you have to test becomes very complicated. So while it's certainly okay to use this feature, it's, you'll want to be careful with how frequently.
Absolutely. I mean, it's a double-edged sword. We say, oh, it's easier because I can add more shapes. Imagine, we haven't shown you how to keep a collection of things, but imagine, just because that capability is there, that I had a whole bunch of shapes and I needed to draw them on the screen or calculate their total area or something. It's really nice to think that someone can come along and add another kind of shape, circle, ellipse, line segment, and whatnot, into the mix, and this code that goes through the collection and calls area on all of them doesn't know or care that more shapes have been added. That's wonderful. But if the person who adds a shape messes up, doesn't just calculate the area wrongly, but makes it incredibly slow, or goes and connects over the internet to consume a web service to find out the area or whatever, the person who wrote the loop originally really doesn't know that their stuff has been hijacked by this new derived class. So where there are natural hierarchies, polymorphism is a very powerful tool, but it can hurt you as well as helping you, and the pain and the glory are both the same thing. It's easy to add new derived classes that do something different, and the original calling code has no idea that you did so. So whether you think that's great or terrifying, it's still the same thing. That's what polymorphism gives you. So if you overuse it, you could end up hurting. Yeah.
Yep. Yeah, and actually, the example that Kate gave is one of the most common examples of where polymorphism is used, is in user interface stacks. For example, in the Windows Store apps, there's a base class UI element. I think it's UI element, and then everything is derived from that. So you have a button base, and then you'll have different types of buttons derived from that. And so in that case, there are a lot of virtual functions. I mean, there's functions to compute the size of things and to do the drawing and to get the current style and things like that. And in that case, it largely makes sense, right? Certainly, there's this opportunity for derived classes to screw things up. But in general, you're still in a fairly constrained environment, and it makes extensibility much easier. And in that, with user interfaces, extensibility is extremely important.
With great power comes great responsibility.
Absolutely, yeah. So that is all we really had to discuss on polymorphism.
It's a very powerful technique that can appear to be magic if you're not following along. And you say, why did this code that thinks it has a shape suddenly start executing? Why is my breakpoint and triangle gone off? Well, that's the purpose of polymorphism. That's what it's for. Good or bad, you need to know that it's happening. But also notice it doesn't sneak up on you. It only happened to us because we were using references. If compute area took a shape, which it can't because you can't have solid shapes, but never mind, we would have had slicing and we wouldn't have had this polymorphism happening. It only happens when you're deliberately choosing to use indirection.
Yep. So, cool, good pointers. So we're going to take another break, and we will be back in 10 minutes, where we will be discussing another form of indirection that complements references called pointers.
And the horribly named RAII.
And the horribly named RAII. Excellent.